Hello viewers, my name is Dr. Rajiv. Welcome to my education channel, YouTube Surgery and Orthopedic Education. Hello viewers, today's online lecture is on stem cell seeding and directed differentiation in tissue engineering and regenerative medicine or TERM. In the end, please subscribe to our channel and give us a like if you find the discourse useful. Also, don't forget to press the bell icon below to get my videos regularly. In vitro differentiation of stem cells into specialized tissue cells is a key aspect of tissue engineering and regenerative medicine. This process is often called as directed differentiation. In this approach, effective and reproducible protocols are used to differentiate stem cells in vitro into a specific cell type or tissue of interest. The concept of cell fate refers to the future identity of a stem cell and its progeny. This is achieved via cell division and differentiation. Cell fate decision is the process by which stem cells develop into a particular fate or a specialized cell type while rejecting possible alternative fates or cell types at the end of differentiation and division. Understanding, predicting, and manipulating cell fate decisions is the main goal of developmental and regenerative biology. Effective and reproducible protocols are used to differentiate stem cells in vitro into the desired type of a specialized cell. Such protocols use chemically defined culture media containing many types of key cell signaling molecules along with cytokines and growth factors. For example, induced pluripotent stem cells iPSCs may be differentiated along the ectoderm and then keratinocyte lineage by addition of retinoic acid and bone morphogenetic protein 4 or BMP4. Alternatively, when cultured on a matrix gel scaffold in defined media, supplemented with ascorbic acid and then exposed to a glycogen synthase kinase or GSK inhibitor, followed by an inhibitor of WNT signaling, the induced pluripotent stem cells iPSCs may be differentiated into immature cardiomyocytes. Factors that influence cell fate decisions and promote stem cell differentiation along a particular lineage include certain biomaterials, the physical properties of the scaffold, and mechanical stress. Such biomaterials may include activin, bone morphogenetic protein 4, BMP4, fibroblast growth factor 2, FGF2, retinoic acid, ascorbic acid, and a glycogen synthase kinase or GSK inhibitor in various combinations and in a stepwise manner. Protocols for promoting stem cell differentiation in vitro often involve steps that mimic normal in vivo development. Firstly, embryonic stem cells ESCs or induced pluripotent stem cells iPSCs are differentiated into either endoderm, mesoderm, or ectoderm lineages, followed by further differentiation into the specific desired cells or tissues through sequential application of some other factors. It is essential to confirm that there are no undifferentiated stem cells in the final product to reduce the risk of tumor transmission. The cells must also be fully phenotyped and their function confirmed. Tissue engineering is a method that combines scaffolds, stem cells, and biological cues or signals or growth factors into a functional construct that restores, maintains, or improves damaged tissues or whole organs. To achieve this, cells are seeded in a 3D, highly porous biomaterial carrier or template or scaffold to allow in vitro maturation, before implantation to improve regeneration outcomes. This process is often known as cellularization. Rapid seeding of viable cells with high seeding efficiency and uniform and effective penetration of cells into the scaffold are the main goals of different methods of cell seeding or cellularization. For example, delivering mechanical stress or electrical stimulation promotes cellularization. Generally, there are 6 approaches for seeding cells into scaffolds. These are static cell seeding, dynamic cell seeding, magnetic cell seeding, pressure and vacuum seeding, using photopolymerized hydrogels, and using bioreactor perfusion systems. A static cell seeding is the simplest and most widely used method of cell delivery, but this is also the least efficient method. It involves depositing a concentrated cell suspension onto a scaffold surface and allowing the seeding solution to penetrate the scaffold with time. The seeding efficiency and penetration of cells into the scaffold are low in this process. The efficiency of cell attachment may be increased by coating the scaffold with various agents. A variation of a static seeding involves coating the scaffold with biological glues such as fibrin or fibronectin to trap cells on the scaffold or to facilitate cell attachment to the matrix or scaffold. The main advantage of the static seeding method is its simplicity. Its limitations are poor efficacy, lack of reproducibility, and an uneven cell distribution. Despite its limitations, static cell seeding is still widely used due to its simplicity and ease of implementation. In order to avoid the limitations of static seeding, methods like application of external mechanical forces such as rotation or centrifugation, application of vacuum or fluid perfusion have been developed to enhance both cellular distribution and seeding efficacy. The dynamic cell seeding method uses techniques that increase cell seeding efficiency, uniformity, and penetration of the scaffold. The scaffold is either rotated in the medium containing the cells, or both the scaffold and the cell suspension are rotated together to generate centrifugal forces. These forces favor the penetration of the seeding solution in the most central portion of the scaffold and enhance cell attachment by recirculating the cell solution multiple times within the scaffold. The high-speed rotational or centrifugation systems have been shown to increase both seeding efficiency and scaffold penetration. These dynamic seeding protocols are highly efficient for thick scaffolds with irregular internal pore networks, increase seeding efficiency, shorten the duration of the culture period needed, and result in a homogeneous cell distribution into the scaffold. In magnetic cell seeding, magnetic forces are used to direct cells into the scaffold. The basic principle of this system is the use of a magnet to attract supramagnetic nanoparticles attached to the seeded cells. The cells are first either labeled with ligand-coated supramagnetic microbeads such as dynabeads or cultured with cationic liposomes containing supramagnetic iron particles. Then a magnet is used to direct the magnetically labeled cells into the scaffold. After a few minutes of magnetic exposure and a 24-hour culture period, seeding efficiencies of over 90% were obtained. This combined use of magnetically labeled cells and magnetic force increased the total number of scaffold adherent cells and improved their infiltration and distribution compared to controls. Magnetic cell seeding offers several advantages over traditional static seeding methods. These are increased seeding efficiency, enhanced cell distribution, rapid graft production, reproducible results, and there is an ability to mimic the histological architecture of the recipient tissue. However, the major concern is that the magnetized particles used may produce adverse effects. In another approach, the cell suspension is forced through the scaffold by differential pressure or vacuum seeding systems to force cells into the pores of the scaffold. As cells travel through the scaffold, they become lodged in the pores and thus seed the scaffold. Pressure differential systems are an extremely rapid means of cell seeding with seeding efficiencies ranging from 60% to 90% and reducing the time needed to seed cells. However, the pressures used may compromise cell viability. Photopolymerization of hydrogel scaffolds is a novel approach to cell seeding. Photopolymerization of a cell suspension in an aqueous monomer solution gives a homogeneously seeded hydrogel scaffold. There are two approaches. In the first, the cells are suspended in an aqueous monomer solution and ultraviolet light is passed to promote the polymerization of the hydrogel scaffold. In the second, an arginine glycine aspartic acid adhesion peptide is used to increase cell adherence to the surface of the hydrogel scaffold. The photopolymerization technique creates scaffolds that mimic the properties of the natural extracellular matrix and gives promising results regarding seeding efficiency, cell viability, and cell proliferation in spite of using ultraviolet light. The production of synthetic tissue constructs which resemble native tissue architecture and microenvironment has great value in regenerative medicine. Complex scaffold perfusion systems have been used to make functional constructs that could mimic the physiologic conditions and biomechanical stresses that native cells are constantly subjected to in vivo. Two types of scaffold perfusion systems are Bioreactor perfusion systems for tissue engineering and whole organ perfusion systems for decellularized organ scaffolds. Using a bioreactor, the supply of oxygen and nutrients can be significantly improved, especially when large tissue engineered grafts are cultivated. Perfusion bioreactors have the highest potential to overcome diffusional limitations for gases, nutrients, and waste products.